And of course, it will be fine to share the slides with people afterwards if they ask for them.
Okay, that's great. Thank you, Dr. Westmoreland. Boa noite a todos. Daremos início a mais um webinar do 23º COBEQ e 18º Envisioning. Primeiramente, eu gostaria de me apresentar. Eu sou o professor Christian Silveira e serei o mediador de vocês no webinar dessa noite. Eu sou, para aqueles que não me conhecem, eu sou professor no Departamento de Engenharia Química na Universidade Federal de Santa Maria. Eu sou formado na mesma universidade, fiz mestrado e doutorado também na mesma e atuo principalmente nas áreas de modelagem, simulação, estimação de parâmetros e equilíbrio de fases. Um foco no uso de modelos de energia de Gibbs em excesso, como os modelos Cosmos-SAC e Unifac. O nosso convidado dessa noite é o Dr. Philip Westmoreland, formado pela Universidade da Carolina do Norte. O Dr. Westmoreland possui mestrado pela Universidade do Estado de Indiana e doutorado pelo MIT. Phil atualmente é professor no Departamento de Engenharia Química e Biomolecular da Universidade do Estado da Carolina do Norte. Sua área de atuação principal é em cinética das reações, com foco em energia, prevenção de poluição e engenharia das reações, utilizando abordagens experimental, computacional e teórica. Dr. Westmoreland é também professor honorário na Universidade Tecnológica de Nanjing e em 2013 foi presidente da AICAJ, o Instituto Americano de Engenheiros Químicos, e também atua como administrador da Kate Corporation, uma instituição sem fins lucrativos voltada para o ensino computacional e tecnológico para engenharia química, da qual ele também foi presidente. Dentre diversos prêmios, Dr. Westmoreland recebeu do Instituto Americano de Engenheiros Químicos o prêmio por excelência na pesquisa em tecnologia de gases industriais em 2017 e em 2019 recebeu o prêmio de distinção na pesquisa do Conselho Alumni da Carolina do Norte. Em 2014, Phil publicou um artigo na revista Frontiers of Chemical Science and Engineering, onde ele traz reflexões sobre o futuro do engenheiro químico e suas renovadas áreas de atuação, como a engenharia molecular, por exemplo. No webinar de hoje, Dr. Westmoreland traz a palestra chamada Envisioning Changes in Chemical Engineering During the Next 25 Years. Não haverá tradução simultânea. Ressaltamos que o professor Phil será palestrante no 23º COBEQ e 18º Envisioning, que acontecerá entre os dias 2 e 6 de maio de 2021 na cidade de Gramado, no Rio Grande do Sul, onde poderá aprofundar ainda mais esse tema. Após a apresentação do professor Phil, teremos um tempo para debate, e as perguntas devem ser encaminhadas pelo chat. Okay, so Dr. Philip Westmoreland, now I'll invite you to give your lecture.
Thank you very much for
You're welcome.
So you see my title. Christian spoke it to you. But let me tell you what I want to talk about will be three things. One, this is really a golden age of chemical engineering. Second, as we look to the future, how will our industries change, our research directions, our education? And then a deeper question, how will the chemical engineering profession itself change? He described something of my background, but let me talk about it a little bit from the standpoint of how it affects my perspective, which is, of course, limited. It's a US perspective, even though I have traveled greatly internationally. But it does include research in a lot of areas, biomass, polymers, energy, fuels. I brought chemical engineering, I brought computational quantum chemistry into US chemical engineering, but also I have worked in government and industry. Union Carbide used to operate Oak Ridge National Laboratory. I worked there, and then in academia since 1986 at two different universities. I've also worked as a program officer, a program director at the U.S. National Science Foundation, and have been a visiting professor in France and UK, and an honorary professor in China at Nanjing Tech. And as he said, I was 2013 AIC chief president. So technical areas, experience, but also another useful source of insight to me has been my wife, because she's a bachelor's and master's chemical engineer and medical doctor who worked at GlaxoSmithKline and other companies. She's worked in startups. She worked in the US Food and Drug Administration. She's an epidemiologist, led the worldwide clinical epidemiology program for GlaxoSmithKline. That has given me a perspective on how the chemical engineering that I do, which is more traditional, interfaces with the chemical engineering that she has always done in biological systems. So predictions. Uh, this is a picture of southwestern US, Monument Valley. The road looks pretty straight, but you can see it starts to swing over, and indeed, it swirls off to the right of the screen there. So it's always hard, but I would argue the best ways to predict the future are to predict from two directions. If we want to look into the future, we need to project from what we know now, and we want to project backwards from needs and for the things that we can imagine. In both cases, what we want to do is to look at this so we can actually shape the future as well as adapt to it. We want to provide for essentials of life and quality of life, health, water, food, energy, quality of life in terms of safety, security, in terms of convenience, things that we would like. So how do we do it most effectively? I want to take each of these separately. I want to start with what we know now, and then move on to what our speculation about the future is. So first, what do we know now? And I would argue that, yes, it's a golden age of chemical engineering. It's a complicated time. Worldwide, we're wrestling with a global pandemic that's affecting things, and yet there are amazing things happening that we can point to. We'll use that and think about, based on what's happening now, what is happening in the future. I would argue that it's a golden age of chemical engineering because of 5 different factors. First, the status of hydrocarbons has changed so much in recent years. Second, biology. Biology has always been around, but it has become molecular in the last 40, 50 years. Third, computing and data have been dramatic changes. Fourth, the way that we do manufacturing goes on as it has for many years, and yet there are big changes there. Finally, the range of people, the range of topics, the diversity of chemical engineering is a great strength. It's greater than ever before. So let me talk about first hydrocarbons. There's a new oil and gas abundance. Looking at the United States, just a map of the shale oil and gas plays in the US, you see that the northeastern US has this huge Marcellus shale field here. But the origin of the shale fracking business was really down in Barnett and Eagle Ford fields in Texas and Permian Basin, and of course the West. And although the Bakken field looks like it stops at the border, of course it does not. This was a US government map, so it didn't presume to include Canadian oil and gas. But this has been transformative. And it's not just the US, it's also worldwide. We can see here's Brazil down here. China has huge reserves, but very few proven reserves. Part of the reason is because even though the gas may be there or may have been there, much of the geology in China, particularly in the south near the Himalayas, is very fractured. How has that affected it? But this abundance of oil and gas transform. It's very hard to look at alternatives when you have a cheap resource that you can use easily. And yet we have to balance it. This was in mid-September, the North Atlantic hurricane picture with 5 different storms going at the same time. There's a great deal of evidence to suggest that these are worsened because of the amount of fossil fuels that are being burned, the amount of carbon dioxide that's being released, on top of the natural generation of carbon dioxide, and affected by the limited amount of capture that the ocean can do. The ocean is actually the largest sink of carbon dioxide. Trees are wonderful, but the ocean's absorption, and that's limited. There are solubility constants. The terrible fires that hit Paradise, California last year and the rest of California this year, the reshaping of the Outer Banks. This is a long, narrow island, and there's a road here that is swamped by the hurricane that came through last year and created 54 new inlets in our Outer Banks. How does that affect things? How can we be resilient to climate changes? Second, biology. As I said, because it's become a molecular science, that's the province of chemical engineers. Chemical engineers apply the molecular sciences. So in many ways, biology has always been a part of chemical engineering, but now it becomes an intellectual core part of chemical engineering as well. That includes the biotechnology side, chemical engineering reactions and separations. Alliances with medicine, though, are a different dimension, where many of the things have to do with materials and transport, pharmacokinetics that are involved. And chemical engineers are playing a big role. North Carolina's largest export industry is chemicals. We have no oil, we have no refineries, but pharmaceuticals are huge. It is the largest dollar export industry. Many chemical engineers from my university go into it. And indeed, we see vaccines based on messenger RNA. An MIT classmate of mine, Nubar Afeyan, is co-founder and head of Moderna, whose trial on the COVID vaccine is supposed to be unblinded in the next few days. They've gotten enough cases to examine whether it's effective or not. Material side, the idea of printing organs. Some of the early work with simple organs like bladders. But this fellow here is a chemical engineer from Michigan State, created a company named Organovo in San Diego, California. It turns out that much of the personalized medicine work is being done by chemical engineers. Why? Because chemical engineers aren't afraid of the math and analytics that are necessary to do the personalized medicine. And chemical engineers can work with others. Chemical engineers are open to learning about things that they didn't learn before. Of course, most good engineers do that. But chemical engineers begin by knowing that they need to do that we need to look at systems. Third, computing. It's not just the computers. Next week, we'll find out who the new top supercomputer in the world is, but as of this summer, the Oak Ridge Summit computer at 149 petabytes slipped to second behind a Japanese computer, Fugaku, at Riken, which is half an exabyte. This is huge amount. And yet, the iPhones that we have would be on the top 5 supercomputer list as recently as 15 years ago. The computing power that we have in our pockets is astonishing, but how do we use it? Well, my point is that it's more than the computers, it's the software, it's the applications, it's the way we do simulation, the way that we network data. Mobile devices, sure, not just iPhones, but iPads, other portable devices, affecting the way that we do work in our facilities, visualization itself, transforming how we work with things, and analytics. Analytics. The term analytics has been around for a long time, but now that we're all working with big data, the use of statistics to analyze and come up with actionable decisions is analytics. That can be operations, it can be monitoring. We've got huge amounts of data, and we'll only have more and more as we digitize more of the information, collect more of the information, and then supply chains. Again, visualization is one thing. You see in one picture here, using analytic software, using spreadsheets, things like that. But on the left, this is the word cloud from an article that I wrote about analytics and big data in chemical engineering, where the size of the letters communicates how frequently an idea is expressed in a document. So ways of seeing the data as well as understanding. And of course, this does carry over to manufacturing. The manufacturing business is transforming now. I'm always amused when I see interlocking gears as a symbol of manufacturing. Wikipedia used not to include making substances as manufacturing, but of course we know that it is. There are activities in the US, the Smart Manufacturing Institute, talking about applying data collection and analytics to manufacturing. The Rapid Process Intensification Institute that AICHE runs for the United States government, which is not only the process intensification, the PI, but it's also modularization, building whole process units on skids that can be deployed around the country, around the world. So how do we do that? Well, it's more than just doing the analysis. It's doing the co-development of products and processes. Smart manufacturing does encompass plant-wide optimization, but also the supply chain, both the upstream supply chain from suppliers to the downstream supply chain, direct customers and distribution centers. Also, sustainability. We know we have to be economically sustainable. If you don't make an economic profit, it's very hard to survive unless there are other factors driving it. But we also need to be societally sustainable as well. We need to be environmentally sustainable because there are costs associated with not being environmentally or societally sustainable. So the net benefit has to be positive for us to be able to proceed. And that includes things like connecting to smart grids, something chemical engineers may not work on, but we know how to work with other people. Finally, I talked about the range and diversity of chemical engineers and the topics that we work in. Let me pull 5 examples real quickly. First would be Frances Arnold. Last year, about this time, she won not the first chemical engineering Nobel Prize. She was doing it on synthetic biology. Linus Pauling, who won 2 Nobel Prizes, was educated as a chemical engineer and chemist, but Frances is the most recent award winner. Bob Langer is co-founder with Noubar Afeyan of Moderna. He's the institute professor of they don't even say chemical engineering anymore. He's the institute professor at MIT and has been in on the startup of nearly 40 different companies, have published nearly 2,000 papers. It's insane. And he's very thoughtful, approachable, and has great perspective. Another contributor, Alice Gast, who worked in colloids and polymeric materials in her research career, is now president of Imperial College London, where she's leading initiatives not only in the UK, but despite Brexit in Europe as well. Another example, Lisa Jackson was administrator of the US Environmental Protection Agency, is now vice president of sustainability for Apple Corporation. And then probably the most famous chemical engineer in the world, internationally known, is Xi Jinping, who is a chemical engineer from Tsinghua University. He's not operating as a process engineer, but he's very much involved in the technical aspects as well as political. Again, chemical engineers use their technical expertise and the rest of their expertise to accomplish what we do. That diversity is key to the contribution that we make. So let me reflect now from the other direction. If we consider what needs we have, consider what we can imagine, let's project backwards from those and consider what might happen. I would mention that the source of this information that I bring here is mainly from a 2015 study that I helped run at the U.S. National Science Foundation and a 2018 study in Chemical Engineering Progress that I co-wrote, but that there's also a National Academy study in the U.S. that I'll talk about at the end of my talk. The 2015 study was saying, how do industry and academic visions of what new graduates should know, how is it the same and how is it different? It was very comforting that many of the expectations were the same, but it's also expectations of new PhDs as well as bachelors and of what faculty should have. Industry and academia have complementary views. In this 25 years looking ahead, this was revisiting a 2008 study where we took 25 people from industry, from academia, from government, junior people, senior people, and explored what would chemical engineering be like in 25 years. At the bottom, you can see there's a link, but if you just Google NSF AICHE alignment, you can get the study on the left. So I want to pick highlights from several of the people who contributed to that study. First, about industry. How will chemical engineering industries change? Billy Barden is Director of Global Operations Technology for Dow. His response was, first, that we would see more demand because of changes in economic power. Economic times are difficult right now with the pandemic. Will it have a long-term or short-term effect? We cannot predict accurately, but still we see so much growth internationally so that we'll see demand for more products that we make. He also sees three different technology areas: process intensification, energy intensity improvements, and zero emissions technology as critical. And when I asked, what industries do you see? He foresees that using landfills as mines for materials, particularly for metals, but using landfills as resource sites is going to be extremely important in the next 25 years. Now, Dow is chemicals, polymers, materials. GlaxoSmithKline, in contrast, is a pharmaceutical industry. And Conchita Jimenez Gonzalez spoke to us about how the pharmaceutical industry is becoming more and more involved in automated algorithms, both for control of processes and for supply chain decisions. She sees the augmenting of human abilities through cobotting, not fusion hybrid of people and robots, but having robotic tools that directly spawn to us. Many robots in industry right now are fenced off so they won't damage people, but cobots would be co-workers. She also sees that these developments will help directly connect to consumers, including the area I mentioned before, personalized medicine, that depends on analytics, visualization, and yes, cybersecurity. I know of reports where different pharmaceutical companies have seen one batch, which may be the year's world supply of a biologic, being destroyed by cyber attacks coming in. Maybe malicious, maybe accidental, doesn't matter. It still destroys a year worth of supplies. This is not the only possibility, though. Jeff Cirola, former president of AICHE as well, was for 40 years the top technology person at Eastman Chemical. He's retired as a technology fellow and now is a professor of engineering practice at Purdue. He argues that industry may look a lot the same, going on his perspective from 25 years ago and from 50 years ago. He foresees that the changes will be more organic. Again, the changes that have come about due to digital computation in design, operation, and control. He does acknowledge there will be new products, but suspects they'll be mostly on the margin, that we'll still be making a lot of the same things and in vastly greater quantities. He does see that the biggest new sectors will be carbon management and then water issues related to soluble salt removal, making the strong statement that that is the next great energy intensive challenge. Another point of view comes from Christina Urdaneta Thomas at 3M, who's senior technical leader for corporate R&D services and operations support. Many ideas, but let me hit a few highlights. One, 3M is substantially a materials company, and the idea of different tools enabling materials platforms, types of materials that can be exploited for a wide range of use. And yet, the ability to customize processes in real time, to adapt the product to the customer, to the order that's made, not being a challenge, but being standard. The idea of having sustainable modular processes, automated processes. Maybe you don't want to have a huge plant making phosgene, but just a localized plant that can make the amount that's needed for the process in operation. Analytics comes up again, not only in general for manufacturing, but in terms of health informatics and material informatics going on. Shifting from industry to education, Mark Birtwistle is an associate professor at Clemson who highlights the idea about the topics that have been taught, that the reason that the curriculum in the United States has stayed much the same for the last 50 years is because it's been adaptable to the changes that have happened. Process engineering, kinetics, thermo separations, transport control for sure. And they come into play if you're dealing with cancer systems biology or pharmacology, synthetic biology, drug delivery. Again, dealing with the data. If we have lots of information, big data, then how do we analyze it? Big data can be largely featureless, massive quantities, like monitoring safety events where you don't expect to see anything until it does happen. Or it could be very complexly nuanced, detailed data. Within that, he sees that biology is permeating chemical engineering curricula as a core science, but it is not yet accepted on the same level of chemistry and physics. He argues it needs to accelerate not just for biology purposes, but because the shift in focus from scale up to scale down may be greatly affected by leveraging knowledge about engineered biological systems as well. And indeed, we held a forum at the AICHE meeting where the people from oil, from chemicals, and pharma said, all of us want engineers who are sophisticated about biology. But it's not just the technology. Julie Champion at Georgia Tech makes the strong point that the importance is having people who are willing and brave enough to take risks, well-founded risk, but risk nevertheless. You can't just solve the idealized problems, but you have to face real-world challenges. And she closes with the comment, how do we instill this behavior in our students? To take risk, to encourage failure and learning from failure, and to step up to lead. Industry echoes that. They want to see people who are technically well prepared, but who can think as well. from that standpoint, chemical engineering is well prepared. The final topic that I wanted to address was how will the chemical engineering profession change? If we look at all the engineering disciplines, we see that they're defined, the core disciplines are defined by their foundational science. If I talk about electricity and electronics, in the US, that would be electrical or electrical and computer engineering. If we're talking about nuclear reactors, nuclear engineering, nuclear physics, electromagnetic physics for the electrical engineers, and so on. And then there are tools that are applied to use them on different systems that are present. That's how the disciplines are defined. And there's the possibility of people being restrained by that, being restricted by that. But chemical engineers, I think most of us who like our profession like it because it is not the edges, but it's the center, it's the core. It's actually being without boundaries to work with whatever expertise, whatever experts we need to work with. In fact, I would argue that it should be the model transdisciplinary discipline. We apply molecular sciences. If we want to look at these three categories, systems, tools, and foundational science, well, we start learning systems when we take our first material and energy balance course. We have to define as a system. Other disciplines don't necessarily start with the systems, but with the tools. We do learn the tools, all these that are mentioned here, but we do it to apply molecular sciences. Even process control is different for chemical engineers because of the natural time scales that occur when we look at, at chemical process systems, whether we're looking at pharmaceuticals or refineries, chemicals, molecular simulations and rheology, computing, or electronics. We use all these tools in very different ways, working with other experts as necessary. So it's that, I think, that's the basis of chemical engineering's future. It's diversity as a discipline. It has to be defined by its core, applied broadly, and not by any boundaries or silos. That should be a model for other disciplines. And that, I think, is the center of where I think we can predict the future. So in my last slide, I want to reflect on this US national study and ask a question. Mine is a US perspective. How does Brazil see the future? This 3-year study that I mentioned is going on. And as we helped to organize that study, I spoke with colleagues in Europe, in China, in the United Kingdom, in Latin America, in South Asia, and in particular, China, Europe, and the UK expressed the wish to show their regional points of view. The US study is a US study. It's a point of view from the US, and yet chemical engineering is not a US profession. It's an international profession. So I raised the question whether Brazil wishes to explore and express regional points of view as well. Christian has expressed willingness to help organize, and we assume that others will be similarly interested in that. It could be simple as a short questionnaire. There could be interest in a workshop to discuss it. The nature of these talks is to prepare for the COBEQ meetings next May that we very much look forward to. I'd be happy to help report. It might be worthwhile to have a workshop at the meeting to explore these issues, but I present that as a challenge to you and have to say I've very much enjoyed this opportunity to talk to you. Thank you very much.
Thank you very much, Dr. Philip, for your amazing lecture. Very elucidative. We will now proceed to the questions from the audience. Is it fine for you?
That sounds good.
Okay. Well, given the advances in technology in the last few decades, with which we can go now from drilling very deep oil reserves to 3D printing tissue cells, what do you think that are the most important subjects and or skills that the new era chemical engineers should learn?
Again, I think the technology of computing and data analysis is important. Just having data does not tell us anything. Information is not knowledge, it is not understanding. To understand it, we need to draw from our scientific tools, from our physical experience. It's very important as we conduct uh, business, as we conduct research, as we conduct education, to make sure that the physical intuition is combined with the technical fundamentals, and increasingly, computation becomes a valuable tool. Going through this pandemic 30 years ago would have been extremely different because video conferencing technology was barely emerging as something that could be done. I remember in 1986 getting an old video camera and hooking it up so I could use an early Microsoft product. The video was terrible. It was jerky, but it had a whiteboard that I could draw information. So the enabling capabilities of computing, I think, are very important. The enabling as far as dealing with data, enabling as far as the sort of analyses that we can do.
Yeah, and I guess that we should also learn a lot of analytics, right? Okay, there's okay. Sorry, would you say something, Dr. Philip?
No.
Okay.
It's the we use. I mean, throughout the world, if you sit in a room, you have to think, well, how many computers are in this room with me? Maybe there's a laptop, or maybe not. There may well be a phone with you. There may be a printer. There may be a microwave oven that has chips in it. Uh, again, it's everywhere. And chemical engineers have long been involved with that and have to stay very involved with it.
All right, I have another question here. Uh, we have been seeing constant efforts in diminishing our impact on nature. Meanwhile, we also have to worry about possible depletion of fossil fuel in the future. What do you think will be the greatest challenges for the new era of chemical engineers, and what role do we as professors have in this?
My expectation is that although we have worried for years about resource depletion, we are going to have resources for a long time to come. We can destroy our planet before we use up all our resources. We know that simply using coal, we have 500 years supply of coal if we choose to use it. But some of that coal is located 1 mile, 2 miles below the earth. To get it out, you will disrupt the ground above it. If we burn that coal, if we burn oil, we'll make carbon dioxide. Probably the biggest hydrocarbon resource that we may have is frozen methane lying on the ocean floor. And yet, there's a huge amount. Time after time, we've heard there's only 10 more years of natural gas, or so on and so forth. It is finite. If the world is to go on for 10,000 years, we don't have 10,000 years of resources to draw from. When will the need become important? It may be driven by forces other than the amount of resources. there is still controversy among individuals about climate change and humans' role in it, because there are natural cycles that happen that change things. There is extremely strong evidence, and AICHE went through a thorough vetting of the studies that have been done and assessed that, yes, there is a very serious amount of evidence indicating that we cannot ignore the fact that carbon dioxide emissions and other emissions are affecting our climate. In some cases, to make it warmer, but in many cases, to make it more extreme. We will see areas that are wet now becoming deserts. We're seeing some of that happen already. California is plainly drier than it used to be, even though it's always been dry. So I see the challenge depends on political willpower as well as technical. I think that's an important message to chemical engineers, that people who are making decisions, whether they are chemical engineers or not, need wise technical guidance. In general, I would say that the public is not so good about understanding uncertainty. It's right or it's wrong. Something is or it isn't. And if a scientist expresses uncertainty, people are troubled by that. Perhaps our biggest contribution, even more than technology, can be helping the public understand uncertainty, risk, the fact that there are few choices that we can make that do not have risks in it. And that includes the use of energy resources, but also chemical resources. I've thought it's terrible to think about burning up all the coal when it's a valuable chemical resource. You can say the same for oil and for gas. So I think we are fortunate to have a lot of resource available to us. To me, the question is, how can we use it wisely? And chemical engineers can help with the technical part of the wisdom as well as the decision process.
All right, thank you very much, Dr. Philip. I would like to thank you once again on behalf of the Brazilian Chemical Engineering Congress team for your formidable lecture and for sharing your time and knowledge with us. Thank you very much.
You're very welcome.
Thank you. Em nome da comissão organizadora do 23º COBEQ e do 18º Envisioning, eu gostaria de agradecer a excelente explanação do professor Phil e ressaltar que durante o congresso esse tema terá uma abordagem mais ampla. Aproveitamos para convidá-los também a participar no próximo webinar, que será com a doutora Cynthia Kuhn-Schulz, gerente de produto na empresa Schlumberger, em Houston, no Texas, nos Estados Unidos, e que abordará o tema Processos de separação por membranas aplicadas ao mercado de óleo e gás. Muito obrigado e uma boa noite a todos.